everyone, welcome back to the Tech Tutor. In today's video, we are going to be diving into one of the most interesting data structures, trees in C++. So ever wondered how we could actually put something like a tree that we just see as a physical object and now be able to store data in it? So that's what we're going to look in today's video, at how amazing of a data structure trees actually are. By the end of this video, you're going to get a good foundational understanding of the trees and be able to implement them in actual life. Okay, so let's have a look. So what are today's topics? So today's topics, again, we're going to see why trees, why do we even need trees in software development, what is a tree, types of trees, and how to implement a tree, and also tree traversals and real-world applications of trees. Okay, so let's start with why trees. Okay, why do we even need trees? So imagine you have a linked list, right? And a linked list has O of n access time, but this is inefficient for large data. Okay, so large data linked list becomes a problem to access the data. So that's why trees offers a better time complexity of O log n, average time for operations, for searching, inserting, and deleting, and all those other operations. Okay, some applications we see them, file systems, expression evaluations, databases, and AI also. So what is a tree? So a tree, it's kind of like a recursive structure with nodes and edges. Okay, so now we're going to go into some terminology of what trees actually are. Okay, so again, if the word recursive over here, if you're not aware of what the recursive is, go and check out my video on recursion. Okay, so now let's start with the first node over here. So this node over here is called a root. Okay, so the topmost node is called the node. And by the way, this is a tree structure. Okay, we start from the top and we go down. Okay, in comparison with what you would imagine trees to be, start from down and go up. This we want to start from over here. Okay, and this, the first node, at the first level is called the root node. Okay, and then so we got done with root. Now let's go with the child node. Okay, so this is the child node, guys. Okay, so the direct connection, this is a child node, this is a child node, and all these are child nodes. Okay, now some of these child nodes are also parent nodes. Okay, so what makes a parent? A parent needs to have a child. Okay, so this one over here, that's a parent and also a child node. Why is it a child node? Because it's the child of 1, and also it's the parent of 4 or 5. Okay, but whereas 3 over here, that's only a child node. It's not a parent node. Why? Because it doesn't have any children. Okay, next, so we got done with parent-child. So now let's have a look at leaf. So the leaf node is the node with no children. So the 6, 7, 8, what you see over here, these are leaf nodes. Leaf nodes. And also 3 over here. This is a child node and also a leaf node. So you can see how it has 2 different characteristics. Right? It's also a child node and also a leaf node. Okay? So the path of a tree is the number of, so say I wanted the path from 1 to 5. Okay, so it's the number of nodes, the sequence of nodes from this node to this node. So I go how many edges? So I go 1 edge and then I go 2 edges. Okay, so this is the path, 2 edges. Okay, whether this is an edge, this is an edge. Okay, next is the depth or the height. Okay, the depth is the path length from root, from the root to node. Okay, so the node root equals 0. Okay, so that's called the depth. So basically, say I want the depth from here to here, it's just basically 1. Now the height is the longest path. It's not just 1, right? It's It's not just going to be 1 in this case. So the height is going to be this entire distance over here. Okay? So this is called the height. So the path from here to here is called the height. So let's do it together. So 1, 2, 3. Okay? So 1, 2, 3. It took me 3 steps. So the height is going to equal 3 for this tree. Okay, some basic terminology that we need to be aware of, because we're going to be using this when actually implementing a tree. Okay, now let's have a look at the different types of trees. Okay, so there's many types of trees. The first tree, it's called a binary tree. Okay, so a binary tree, in the further slides, we're going to look at the of what these actually look like. Okay, so each node has lesser than 2 children. Okay, either side. Okay, binary search tree is where the left subtree has lesser nodes than the root, and the root has greater nodes than the right subtree. Okay, so basically what I'm trying to say over there is it can only have maximum 2 nodes. Okay, it cannot have more than 2 nodes. Okay, so and that's called the binary search tree. And AVL tree is we also call it a self-balancing binary search tree, so it balances by itself. And again, I'm just trying to give a basic trying to let you know that these types of tree exist. We're gonna talk more about these in the further slides. So a heap is kind of like a tree, one of these a binary. It's kind of like a binary tree, but it has it's kind of like a pyramid. Now when you think of it like a pyramid tree, it's a prefix tree. It stores characters, paths, forms, words. And B trees, they can have more than 2 children. Okay, so let me get to the next slide and explain these. Okay, so a binary tree. So this is a binary tree where you see over here. So you could see each node has lesser or equal to 2 children. Okay, so not more than 2 children. Okay, but it can have lesser than 2 children. So this one has 2 children. Okay, 7 has 2 children. 6 has 2 children. Okay, 9 has 1 child. 9 has and then this 9 over here has 1 child. Okay, so again, this is called a binary tree. And where do we use this? We use this in expression trees. Okay, expression trees are where we have where we can have, instead of 1 over here, we can have plus a. Okay, so when we're trying to add, right? So we can have an expression that we can form through these trees. Okay, and also compiler parsing. Okay, when the compiler actually takes in our code, right, and how it compiles our code, right? So we're actually seeing things. We're seeing data structures that are able to do this, are able to process our information, which is really interesting. Okay, next is a binary search tree. Okay, so a binary search tree is one where the left subtree is lesser, the nodes are lesser than the right, the root, and the root has lesser nodes than the right subtree. Okay, so this has by the way, this what I'm talking over here, right? This I'm talking about the data. So the data in the node. Okay, so you see over here 40 over here. 40 is greater than 30. Okay, but 40 is lesser than 50. Okay, do you see? So the left node, what I'm trying to say over here, so the left node, it's gonna be smaller than the current node, whereas the right node is going to be greater than the current node. Okay, as you can see over here, 40 is greater than 30. 30, if I go left, right? If I keep going left, I see that 30 is greater than 25. Okay, but if I go right, I see that 50 is greater than 40 now. Okay, but also if I go right, 60 is greater than 50. Okay, so this is a binary search tree. Okay, so this helps us find data even faster. Okay, so it has an O of log n average search time. compared with if you've come across searching, right? With linear search, it has a bigger time complexity, and binary search has O of log n, right? Remember, linear search can take O of n, okay? But binary search, right? It's much more. It's better. It has O of log n average search time. Okay, sometimes it could degrade to O of n if this, right? It's unbalanced. Okay, if it's unbalanced, right, this tree, then it could degrade to O of n. That's why we want to make sure our binary search tree is balanced when we're trying to put data in it. Okay, so when I mean balanced, so the left node has to be lesser than the current node, and the right node has to be greater than the current node. Okay, now let's talk about AVL trees. These are also really interesting trees that I personally love learning about. So this tree is kind of like a self-balancing tree, and the difference between, right, the nodes, it's only one. It's going to be one. Okay, it's going to be 1. So the difference between this level and this level, you can see if I say 0 over here, okay, just to start with 0 and 1, if I subtract it, it's going to be 1. But say I had another value, say I had 3 over here, right? But now if I start from 0, if I 0, 1, and 2, you notice now I have a difference of 2. Now this is when I would need to balance the tree. And in another video, we can see how these rotations happen. There's some rotations called left, 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 right, right, left, right, and right, left. So those are the specific types of rotations that we could see in AVL trees to balance this. Okay, so the good part is it guarantees O of log n worst case operations. Okay, so that's a good part of AVL trees. And the use case is in databases where query stability. Okay, say you're trying to find something, right, and you need your database to be stable. This is where this is where AVL trees matter. And you will see many of these data structures are actually used in databases. Okay, so that's AVL trees. Now let's talk about heaps. Okay, heaps, as I was saying in the intro slide about data structure, about all these trees, it's kind of like a pyramid. Think of it like a pyramid. Okay, the box on the top, it's always gonna be either the minimum or the maximum of these nodes, of the bottom nodes. Okay, so say I have 1 over here and it's a min heap. That means that all these values over here are gonna be greater than 1. So all these values in these nodes. So let's say this is a max heap, and say this, I put this as 5, right? All these nodes are gonna be greater than 5. Okay, now this over here, guess what this is? I'll give you 2 seconds. You guessed it right. This is a min heap. Okay, as you can see, 1 is lesser than 2, it's lesser than 3, it's lesser than 4, 5, and 9. Okay, so where do we use this? Priority queues, we use it. We also use it in an algorithm called Jigsaw. Okay, algorithm. Okay, priority queues is another type of data structure that we also use. And now let's talk about tree. A tree, this is what it looks like. It's nodes, right? The nodes of a trie. We call it a trie actually. Trie. Let me correct the pronunciation. Trie. It stores characters. Okay, and each of these characters, right? The path, right? The path to those characters, it forms a word. So as you can see over here, A and D, and then we got and over here. So A and T, we got ant over here. D A D, we got dad over here, and D O, we got do. So you could kind of see how useful these could be when we are trying to do. Oh, you can see this in autocomplete, right? The autocomplete that we kind of get bugged of in our phones. It's this data structure. Spell checkers in our Google Doc that we have, right? How it spells words. You might be wondering where it gets all those words from. It's these types of data structures that make it easy for that quick spell check to happen. Okay, so storing. So we wanted to store cat, car, all these different words, right? We could use a trie data structure. Right? Okay, so a B tree and B plus trees are those trees that could have more than 2 children. Okay, one really good thing about these trees is they allow indexing to happen, and they're really useful in databases. Okay, they're also useful in file systems like NTFS and ext4, and they're optimized. So why are they used? Is because they optimize for disk access. Okay, so they minimize the input output that needs to happen. Okay, so if you want to access, they reduce the input output operations that need to happen. And these, as you can see, it has more than 2 children, not just 2 children. It has 3 children over here. So this is a B tree, and this is a B plus tree. Okay, now let's look at the implementation of a tree. How do we implement this? So let's go to our VS Code. So here, I'm gonna create a tree.cpp class. Okay, I'm gonna create a tree.cpp class. The tree dot, we don't need that right now, so delete that. Okay, so tree.cpp. Okay, so first I'm gonna include IO stream. Okay, I'm gonna include using namespace std so that we don't have to worry about doing the std stuff. I'm gonna create a struct for our node. Okay, because now remember we were trying to create nodes, right? So we need, so what does a node contain? So we know a node contains data. It has reference to the left, whatever it's pointing to the left, and also whatever it's pointing to the right. Okay, so it has a pointer to the left node, and it also has a pointer to the right node. Okay, so now we're gonna create a method node, create node. So we're gonna create a node with some data we're gonna pass through it. Okay, so that data, so using that data, we're gonna create a new node. Okay, and that new node is going to point to the new node. Okay. You don't need that new allocation. Okay, so new node, its data, right? Its data variable is gonna point to this. Okay, and when we do that, what we're also doing is we're saying that the new node that we just created, its left node is gonna equal a null pointer. Okay, so we're saying that its right node is gonna also equal a null pointer. Now we could reduce this code a bit, and we could just say left node equals the right node is gonna equal null pointer. Okay, so I want to imagine this. So imagine we're creating a node. So that's okay, a node that's pointing. So let me open up a slide to show you. Okay, so we're creating a new node. Okay, and when we're creating a new node, we have some data in it. Say I put number 7 in. Okay, that's what we're doing in our code also. Putting data in it first, then we're saying that its left, it's gonna be null pointer. It's gonna be a null pointer, and its right node is gonna also be a null pointer. Okay, so why do we put them as null pointer? Is so that when we want to add something to this node, right, we could just say that this is equal to, let's say, 5. Okay, this data, right, left node data is equal to 5. Okay, now if we want to do the same thing, we're going to keep doing that. As you can see, I'm going to create a left node, right node. Okay, and I'm going to put null pointer first. Okay? If you have any questions, please leave them down in the comment section below so that I could, I'll get back to them as soon as I can. Okay, so here we've done left node equals right node equals null pointer. Okay, next is, we gotta return that node, right? Important, we gotta return that node. Okay, and in our main method, we're gonna create a root. We're gonna say root node equals create node. We're just gonna create our node, and we're gonna say root left equals create node. Let's say 2. Okay, and root. Oh, we gotta put a number over here. So okay, let's say we put 1 over there, and we say left is equal to 2, and root right equals 3. Okay, I pass in 3. So okay, so now what this is gonna look like, right? So we said root. Okay, let me open up. So let me say over here. So we said 1. Initially created 1. And what do we say over here? We said left is going to equal to 2 and right is going to equal to 3. So this is what we're actually doing. Okay. Now what if we want to add a node to over here to the left of 2? Okay. What we're basically going to do is left node. Let's say it's going to equal 5. Okay, well, that's what we can do. Okay, so we're going to say root left is equal to create node 5. Alright guys, so that's how we're creating a tree. That's how we're implementing a tree. Understand that we need to know what a node contains, where that node is going to point to, and how we're going to create that node. Okay? And understand the pointer principle, like how we're creating pointers. Okay, so let's get back. Now let's talk about how we're going to traverse a tree. Okay, so let me create some nodes over here. Okay, say this is our tree. Okay, now I put in 2, 0, 5. Okay, so let's say that's our tree. Now we need to know, if we want to print out the tree, we need to know how to traverse it, right? There's many ways, and among those many ways, these are 3 ways: pre-order, in order, and post order. Okay, so now if we want to do pre-order traversal, right? First we take the data. Okay, so we're gonna first have a look at data. So I'm gonna put D over here. Then first, so data. When I say data, that means we're gonna print them out. Okay, in this case, we're trying to print out the traversal, right? The traversal of the tree. So data. Then we go left. Okay, so left, okay, and then we go left, data. Okay, now we're gonna print out 0, and we're gonna go right. So DLR stands for data left, right. So go right, we don't have anything. Okay, so data, the data left, right, and right, and then we go back over here, and then we go right. Okay, so we're gonna do data. We don't have anything on the left. We don't have anything on the right. Okay, now let's say we do in order, right? In order is left, data, right. Okay, so we're gonna go left. Okay, left we don't have anything. Okay, now we're gonna do data. So I'm gonna print 0. Data we have finished. Right, we don't have anything. So we're gonna put R over here. So, and I'm gonna go up, back away, and I'm gonna do data over here. So 2, and then right. Okay, right. Now I'm gonna do left over here. We don't have anything on the left. Data 5 and right. So we don't have anything on the right. So this is in order. And 205 that we found was pre-order. And post-order, that's gonna be left, right data. Okay, so we're gonna say left, okay, left, okay, and then we're gonna go right. We don't have anything on the right, okay, and we're gonna say data. data. Okay, here we're gonna go back, right. Okay, right, now we're gonna go left. Over here we don't have anything on the left. Right, we don't have anything. Then we're gonna say data. Okay, so 0, 5, and then we're gonna go back. Data 0, 5, 2. Okay, so this is what it looks, guys, for this tree. This is what our data, what our numbers actually look like. Okay, now in another video we could actually see what happens if we have bigger trees. Okay, say if we have more nodes, like 1, right, 3, right, 6, 7. Okay, I have more nodes, right? What would happen in that case, right? And that's that. It gets more interesting to see how that actually turn out. Okay, so pre-order, the use case is in listing directory structures. Okay, in order, it helps in infix expressions like a plus b times c, like how where the b times c should go first, right? According to the rule of BODMAS or PEDMAS, if you've learned about that rule. Okay, so it's gonna be a plus brackets b times c. Okay, so how the computer does that, right? And post order is calculating directory sizes, basically. Okay, let me know in the comments down below if you have any questions about this. So coming to some real world applications of this is of trees in general is hierarchical data directories, like how we know the C, like our C directory that we have in our computers, desktop, trees.cpp, how it stores that, right? In the C drive, right, we have a desktop folder. In desktop folder, we have trees.cpp that we just created, right? Okay, so databases. So if you want to do indexing for a fast search, okay, like how you have on an Amazon website, like how you would search something and it just shows up so fast, something that it's really close to what you were actually searching for, right? So all these searching, right? Searching websites. It's useful these times of the trees, right? Compilers for parsing trees for expression evaluation, right? If the compiler needs to evaluate our syntax of our code, right? So that's it. It uses the syntax rules and parses our code through that. Okay. Coming to conclude this two-part video, guys, trees enable efficient hierarchical data management. From traversing, searching, inserting, you're gonna see this in a lot of places. Okay, as I was saying throughout the slides, I was talking about databases, like how even when you go on Amazon and YouTube, all these like places where you basically search and like it pops up that most relevant thing to your actual search. The trees goes into usage over there. Okay, guys, if you did like today's video and this two-part video, please do like, share, and subscribe. Leave a comment down below if you have any questions or would like to see something. Thank you. I hope you have a